good morning, good afternoon, good evening, whatever time you're watching this educational video. Today we will be knowing the basics of sinusoidal wave, or others will pronounce it as sinusoidal, but yeah, I prefer to say sinusoidal wave. And in the picture here in our screen, this is the so-called how sinusoidal wave looks when we plot it or when we graph it. Okay, so it looks like a typical transverse wave, but it must be perfectly having the same amplitude in the positive, upward, and then negative direction with respect to regular time interval. Okay, so before we will begin knowing the basics of sinusoidal wave and compute some calculations related to the problem of this kind of equation to be given by a sinusoidal wave, don't forget to, yeah, of course, subscribe this channel. This is really related to the simple harmonic motion in which it needs a, as we all know, it needs a restoring force uh, to, to be classified as a simple harmonic motion. This is really a great factor for us to know that this kind of motion is SHM, or simple harmonic motion. We need the restoring force that will always bring back the moving object or the oscillating object into its equilibrium. Okay, we have known that we have two systems in or studying the simple harmonic motion, or we have systems that exhibit the SHM, or the simple harmonic motion, with the restoring force. Of course, the first one, we have the spring mass system, in which the spring is being stretched, and then as it is being released, it will move back and forth. So the type of wave that is being exhibited there in terms of the direction of motion, that is parallel to each other, right? If you could still recall, that's a longitudinal wave. So it's moving back and forth. As you imagine a spring moving back and forth. Okay. Once it releases, it will go there and it will go that direction repeatedly, especially no friction. Okay. And another one is a pendulum. Either it's simple pendulum or compound pendulum. It approximately like follow a motion of like a transverse wave. So we put it here, transverse wave. A pendulum swings side to side, going to that direction or in this direction, going side to side, perpendicular to the downward pull of the gravity. So something to do with transverse wave. But these two, either longitudinal wave or transverse wave, whatever the type of wave in terms of direction of the motion, like for example, in a transverse wave, like in our pendulum, it is a type of wave wherein the particles move perpendicular to the wave's direction, 90 degrees. And while our spring mass, it will moving back and forth, it's a kind of longitudinal wave, another type of wave where particles move parallel to the direction, just like sound energy, for example. These two systems, the spring mass and the pendulum, with different types of wave in terms of the direction of motion of its particle relative to the direction of the wave motion, longitudinal or transverse. When we plug them, I mean, when we plot or graph them out, it will lead to this. I will draw it or try to observe or try to think that the amplitude upon going upward is the same going downward, positive, negative, positive, negative, positive, negative. But it doesn't look good, but it must be same in amplitude. Amplitude is as we all know, amplitude is the height of the wave from this point to this point, or from this point to this point. They will have the same height in meters. We call it this kind of waveform. If we graph the motion of the spring mass and the pendulum exhibiting the simple harmonic motion, this is what we call the sinusoidal waveform. So sinusoidal wave is related to simple harmonic motion. All right. All right. So let's try to know the equation that is very popular. It is a derived equation comes to dealing with a sinusoidal waveform. And remember, this kind of a waveform is exhibited when a motion of the object is like back and forth in a regular time with a restoring force. Most probably with restoring force, it you know it will have a waveform like this or the sinusoidal wave. The equation, please take note that we have this equation y is equal to xt, y of x of t is equal to the a sine, then we have the kx minus the omega t plus the phi. Yeah, you're correct. That's phi. Okay. And we will try to know what are these variables here. It relates the sinusoidal wave. Let's begin with the y. Y is the height in meters from equilibrium. The equilibrium is this line here at the center. This is going to be our equilibrium. And as the object moves back and forth, so it goes up, down, up, down, up, down repeatedly in a perfect time interval. And if you notice here, I will use another color for this. The distance between the equilibrium and our point where the sinusoidal wave begins to move, or yeah, this is our y distance from the equilibrium to the certain point where the oscillation um, or the plotting of this up down motion begins. That's the y. All right. If you have wonder xt here in our equations, just the position and the time, because time is really there as the motion repeatedly the motion repeats itself periodically or in simple harmonic motion. Yeah, the time is needed for our equation here, and in what position in particular. Now we have a. A is the amplitude of the wave. As we know, amplitude is like the height of the wave. Let's say, for example, from the equilibrium to the that peak, right? And you could also have, yeah, try to think this is perfectly done, but it must be in the same amplitude as it goes up and down. But my drawing isn't, giving that kind of feeling or impression. So assuming it's the same from that equilibrium downward to that peak, as well as here, it must be in the center, but yeah, it's okay. That's the amplitude of the wave. We have two amplitudes here if we will try to continue it this way, assuming that it's along the height of our point here. Now, if you could still recall this point here in the like positive part of our graph here, this point is the crest, right? And the bottom part, it's like the negative part of it, it's the trough. Please recall that one. All right, and we have the k. K is called the wave number, and it is represented by this equation. K is equal to 2 pi and then lambda. That's a Greek alphabet letter. So 2 pi over lambda, that's going to be the wave number or the k. And if we try to locate the lambda here, it's like the distance between from one crest to another crest of the waveform. So it's here from this to this part. This is your lambda, the distance between crest to crest, or if we have to continue our wave here, so from trough, distance from trough to another trough, this is also the lambda. Or simply we call it, if you could still recall the basic of the anatomy of the wave, it's the wavelength, right? Wavelength could be trough to trough, crest to crest. We have x here. X is the position position of how far the motion from the origin. So this is our origin here, the very beginning, where the sinusoidal wave generated. So the position from that particular point of our sinusoidal with respect to the origin, that's the x. It should be in meters, as well as our y here. Y should be in meters as well. Our amplitude should be in meters also, stuff like that. Now we have the omega here. Omega is not the angular velocity, but this time it's going to be the angular frequency. All right, angular frequency, if you could still recall one of its equation, we can have angular frequency is equal to 2 pi multiplied by the frequency. All right, and we have t for the time in seconds. In the last figure here, in the last variable here, we call it as I mentioned earlier, we call it as the phi. It's the phase constant. The phase constant defines the initial state of the waveform at the origin of time and space. Yeah, it's at the origin itself. And then another thing, we can say phase constant is the specific starting point of the wave cycle at that exact moment measurement begins. So whatever we put it here as the phase constant, yeah, in any exact moment, the measurement begins. But most of the time, to have a clean interpretation, it's the beginning from the origin itself. Okay, so let's try to know all of these variables. It's better to really understand them with a problem.